Welcome to Empowered Learning. This video will be about the dot product operation for vectors and how that fits within the world of vectors. I'm going to split up this topic into two separate videos. This first video will be about the theory and properties that go along with the dot product. We'll also be doing things like deriving the dot product and showing where it comes from, and some of the conceptual nuances of this particular operation. The second video will just be going over regular textbook-like examples, applying the concepts that we learn in this particular video. So recall that in learning the basics about vectors and their properties, that we discovered the concept of multiplying two vectors together was not a straightforward task. Since performing this action on two vectors would need to account for both magnitude and rotational effects at the same time. And so I mention this because in the video that I did on just basic vectors and what they're about and their basic properties, one of the things that I mentioned in that video was that the notion of multiplying two vectors together was something that we just couldn't quantify or take in account of with one operation. So that's why I started off this particular video saying that. Now, another thing that I didn't mention in that video on the basics of vectors is that I was going to go more into detail on why is it that whenever we try to quote unquote multiply two vectors, what that means conceptually in the world of vectors, why we had this magnitude and rotational component that we had to simultaneously account for. Okay, so to do that, I'm going to show you an illustration here. Now, I'm not the best artist, but hopefully what I've drawn here will kind of get the point across. So the basic idea is this. We have a situation where we have a ball that is traveling with some kind of, velocity. Okay, so let's say it's rolling down a hill or rolling uphill or whatever. Okay, the path of this ball I have here with this dotted black line here. So you can assume that it's kind of rolling downhill, and right at this point is getting to the point to where it gets to the bottom of the hill and is about to roll back up. So that's kind of the idea of the ball here that we're talking about and its path. Now, if we looked at this ball rolling along this path that I'm showing you here at a snapshot in time, we're going to imagine that we have one of two forces that may act on that particular ball. To put it in layman's terms, something is going to strike the ball with a certain kind of force. Now, the force that we're talking about here, even though I'm using the word force, what we're really going to refer to in terms of the quantity of the thing that the vector is measuring is going to be velocity here, just to make this a little bit more simple to follow. So we have a ball here. It's going along a path, and at some snapshot in time, roughly about right here, sometime t equals a, we see that either a force F1 with some velocity or a force F2 with some velocity acts on it. Okay. At this snapshot in time, this ball that is here, if we looked at it and said, all right, if we were to be able to continue on that particular track for this instant in time. So let's say this ball kind of breaks off the path and it keeps on going. It would go in the direction of this vector v here. Okay. Now, of course, this vector minus v is just that same direction, but that same vector, but in the opposite direction. Okay. So when we have this ball being acted on by either a force F1 or force F2, we can say here that, of course, if this force is going all the way through here, that alpha, which is this angle here, is going to be the angle that is going the angle that's going to be created by the actual force, the direction of the force itself, relative to the directional force of the ball at that snapshot in time. Okay. So remember, V is the vector at the snapshot in time here. A more formal way to say that is that the direction that the ball is going at that instant is parallel to the tangent line made with this particular path and the line that could, possibly represent that vector. Okay. So this vector V, I mean. So the point that I'm trying to get at here is that depending upon the angle in which the ball is striked at, the ball is going to do two things. One, this force is going to transfer some of its velocity over to the ball. Okay. So if it hits it at a certain angle, one of the things that we know is that depending upon what angle it gets hit at, there's going to be a certain amount of that force being transferred from whatever object that is that hits it with that force to the ball. Okay. The next thing that we know that happens is that if it hits it at a certain angle, this ball is also going to rotate. Okay. And so if you think about, let's say, two cars, they get into a car accident at an intersection. Okay. When one of the cars hits the other, it's not just, the car just hits the other car and that's it. And, the other car just keeps moving, with a faster or slower velocity or whatnot. Usually one or both of the cars ends up spinning as well. Okay. And so that's that rotational component that I'm talking about. So if we take this ball and we apply, let's say, force 1 to it, one of the things that we know is that this angle here is telling us that when this force hits the ball, this ball is actually going to be rotating in a clockwise motion. Okay. If it's hit with force F2, then we're going to see that this motion now is going to be counterclockwise instead of clockwise. And of course, the ball here is going to be spinning on a vertical axis. And the way that I've drawn this is I've drawn it as if we were looking overhead here. So you can imagine that this point or this dot that I have right here is the positive z-axis sort of shooting out of the page towards you, okay, or shooting out of the screen towards you. So if you look at it from that standpoint, we see that the ball, if I hit it with force F2, should be spinning counterclockwise here, okay? And if it's hitting with force F1, it's going to be spinning clockwise, okay? Now, the main point that I want to get at here, again, is that whenever a force is acting on a ball, or we could say a particle or whatever like this, when that interaction happens at that moment, there are two things that are simultaneously happening. One, there is a transfer of magnitude of the force that acted on the ball, to this vector V here that's basically describing the direction in which the ball was going at that instant. So there's a transfer of magnitude. So depending upon if the velocity of force 1 was larger or smaller than the actual magnitude of the vector V, the overall new magnitude of that new vector V that's going to come out as a result may have a magnitude that's bigger or smaller than it was before. Okay. So that's one thing. The next thing, again, is the rotational aspect of it. We know that this particular ball will end up rotating depending upon how we hit it. Okay. And now, in all actuality, I know the way that I have the force is written, it looks like it's going through the ball per se. But really what I'm trying to simulate here is that, let's say F2 could hit the ball on its side here. I didn't quite draw that well. So let's say it could hit it on the side here. And the point that I'm trying to make is that this force F2 is going to be parallel to the one that I'm drawing here. So it will really be like this, but I just try to draw it to make it look a little bit more simple. Okay. Same thing with F1. I could actually, that didn't go so well either. So I can actually draw it like this to try to make it, parallel to the one that I've drawn. Okay. All right. So my main point again for bringing all this up is that because we know how vectors act, we need to be able to have an operation that will quantify both the magnitude and the rotational effects at the same time. And unfortunately, with multiplication being a binary operation, like how we're used to working with it, it just won't be able to take on both of those tasks simultaneously. So what we do is we say, all right, well, vectors has both this magnitude and this rotational component to it. Let's make up an operation that deals with just the magnitude aspect of it. And that is what the dot product will be. If the rotational aspect of how vectors interact with each other whenever we do this multiplying them, that is what the cross product will be. And so the video that I have on cross product will go into detail with that. All right, so just to summarize before we move on here, of course we have this ball, forces F1 and F2 are being acted on it. The force F1 is a vector representing an outside force that strikes the ball with some velocity. And we're going to call that the magnitude of F1. F2, same thing, but it's going to strike it in a different place. Alpha is going to be the angle in which F1 strikes the ball at a single instant in time relative to the path of the ball or the direction of the ball. And normally when we talk about the direction of a vector, we normally say that in terms of the unit vector. Okay. For our angle beta, it is going to be an angle in which our force F2 strikes the ball at some instant in time, and it's going to be relative to the same vector here. But really, because of the nature of how F2 is and what that vector is, even though I put just a regular unit vector, it would actually be this vector here. Okay. All right. So as I mentioned before, when my vector F1 strikes the ball at some angle A, a portion of the magnitude of F1 is going to be transferred to the ball. Okay. Also at that instant in time, the ball will be on the same path as the direction of vector V, which is basically that unit vector. Same kind of thing for F2. When F2 strikes the ball, it's going to transfer some of its magnitude over to the ball. Also, we know that the ball will be on the same path as the direction of vector minus V. Okay, and that's because of the fact that the angle beta there, and even though I use it as a reference angle, the angle beta there is such that the direction of the actual outcome should be negative. Okay. All right. And let me go back here just to kind of clear that up. I use the angle beta here, but this angle beta is actually like a reference angle, and we can actually use that to be able to do it. Normally you'll kind of see something like this, and I'm going to erase this just to kind of make my point here. And this will kind of explain why we're saying that we're actually looking at things in terms of the vector minus V here. So let's say from this vector, if I went to here, let me call that beta star. Okay. So that is what the actual angle will be in between vector V and vector F2. Okay. Now, of course, what beta is just a nice convenient way of saying, hey, you know what? I can also measure it as the angle in between F2 and minus in the vector minus V. Okay. So saying it as the vector in between F2 and positive V is the same thing as saying the angle using this angle in between the vector F2 and minus V. Okay, so you could express it either way. The more traditional way to do it is the way with beta star, but I tried to write it in a way to where it would make more intuitive sense. So that's why I made the angle beta sort of like a reference angle. All right, so moving on here, we know that the measures of angles alpha and beta will constitute how much of the magnitude of force F1 or F2 is going to be transferred to the current velocity or the current magnitude of the velocity vector V of the ball at that instant in time. Okay, so in other words, all I'm saying is that based upon the angle at which the force strikes the ball, that indirectly tells us how much of the magnitude from those respective vectors would transfer over to the ball on the path of vector V. We also know that if F1 strikes the ball will inherently rotate on the vertical axis, like I told you before. And if F2 does the same thing, it will rotate. When F1 does it, it's going to rotate in a clockwise manner because the angle is kind of like this. When F2 does it, it's going to rotate in a counterclockwise manner because the vector points that way. Okay. Now, the last thing is that the velocity at which the ball will rotate about this vertical axis will be largely due to the transfer of the magnitude of either vector F1 or F2, depending upon the one that we're dealing with. So my point here is that even when we talk about the rotational effects in the video where I'm going to address cross product, you're still going to see that there is a magnitude transfer going on there. It's just that the difference is that magnitude transfer will refer to the motion along a vertical, along the vertical axis there, which will end up being perpendicular to the forces that are acting in the plane where we're talking about the dot product. Okay, and again, I'll get more into detail with that in the cross product video. So here from our illustration, we note that observations 1, 2, and 3 that I went over solely deal with the magnitude effects of multiplying two vectors together. And observations 4 and 5 solely dealt with the rotational effects. And of course, our issue, again, like I stated before, there is no binary operation that can simultaneously account for both the magnitude and rotational aspects of the example that I've given. Now, the solution, we need to come up with a separate operation that sort of embodies the concept of quote unquote multiplying two vectors together, but one needs to have a magnitude aspect to it. One needs to have a rotational aspect to it. And of course, like I said before, the dot product is going to take care of the magnitude effects of multiplying two vectors together, and cross product, which we'll talk about in another video, takes care of the rotational effects. Okay. Now, I know I've taken a while to explain all of that, but by taking the time to kind of go over that and reiterate things is actually going to make going over the actual concepts that we need to learn here a little bit easier. Okay. And it's going to make it more efficient to kind of process all that information too. So that's why I took so much time to, sort of repeat myself. All right. So in this set of notes here, and of course I'm doing a video over the notes. We're going to learn about the dot product operation, and of course a cross product operation. You can see the video on that that I'll create later here. Now, what is the dot product? Okay, so the dot product, which is notated like this for any two vectors u and v, and of course this is what u would look like in 2D space. This is what u would look like in 3D space. I've just written it as component vectors. We pronounce this u dot v whenever we read it, and of course we're assuming that u and v are vectors when we say that. So we see that the dot product in 2D space just ends up being the the sum of the product of the components of each vector. So u1 and v1 are just the components of the first component of u and v, and u2 and v2 is the second component of u and v. Multiply them together, add them, that's what we get. Of course, in 3D space, we have a third dimension, or in this case, the z coordinates to worry about. So that's why we have the u3, v3, okay? So now we need to talk about, well, where does the dot product operation actually come from, okay? And so we know here that the dot product operation actually is a byproduct of wanting to know the angle in between two sides of an oblique triangle, or really we could say any triangle for that matter, but for what we normally use this for, and you'll see in a minute why I'm saying this, we normally just consider oblique triangles, which are just triangles that do not have any right angles in it. Okay. Now, if we assume that the sides of this oblique triangle here are directed line segments, then by definition, we could look at the sides of this oblique triangle as a vector, because we know that the most simple definition of a vector is it is a directed line segment that starts at some point, ends at another. Okay. So if we take that into account, and we recall that the law of cosines is an identity that allows us to be able to know the relationship in between the sides of a triangle and an angle in between two sides of the triangle, two sides of the three sides of the triangle, then we know that we could rewrite that law of cosines formula this way, okay? And to kind of make my point here, let's say if I had a triangle here, let's say this is alpha, beta, and gamma here. That beta doesn't look too hot. I'll make this a little bit bigger. Let's say this is alpha, beta, and gamma. And let's say this is A, B, and C here. Then, of course, we know that the law of cosine says that A squared is going to be equal to B squared plus C squared minus 2BC times cosine of alpha here, okay? And so if I was to rename this triangle here to where now this side is W, this is U, this is V, and let's say for simplicity here, instead of having alpha there, I have a theta here. Then of course now this ends up being W squared is going to be equal to U squared plus V squared here. And that'll be minus 2 UV. And this will be cosine of theta instead of cosine of alpha. Okay. And so, of course, we assume that W, U, and V in this case, not the case that we're going to be doing here, but in this case are just the lengths of the sides of this oblique triangle. Okay. Now, in terms of vectors, of course, a vector is a magnitude with some direction, or in this case, a length in some direction. We would think of this as the magnitude here, okay? And of course, this one here, we'll think of that as the magnitude. So if you look down here now you see why this particular formula, in terms of how it relates to vectors, will look like this, okay? So now that we have that, our goal is we want to figure out, well, what is this angle going to be? Much like how we would if we were applying law of cosines to this triangle that I've drawn here, and we say hey, let's figure out what this angle theta is, given that we know the magnitude of u, magnitude of v, and magnitude of w. Or put another way, if we know all three of the sides lengths, we can figure out what the angle is. Okay. Now, from here, we see that there is some collection of calculations that we need to do. The first thing is that we realize that the magnitude of u, v, and w, which represent the lengths of the sides of the triangle, would be the same as sides AB, AC, and B, and CB. Okay, and that is because if we go back up here to figure A, I've labeled them such. Okay, we got AB here. That's basically what vector u represents. AC represents vector v, and of course CB represents vector w. Okay. Now, another thing that we see is that this vector w here actually, if we use the parallelogram law, it is actually the resultant of the vector u minus v. Okay, not u plus. It's actually u minus. And so here to kind of make my point, if we use the parallelogram law here, I'm going to change colors here for just a second. So if I come here, and let's say if I did this, then of course, this would be over here on this side, this is like me saying u, vector u plus vector v. The resultant of that would be this vector here that I'm drawing. Okay. But of course, that's not what w is. Okay. In order for me to get what w is, I would actually have to switch v being the other way. So that's why I have it like this. And of course, this vector u, I would have to slide to being over here. And so that's why I have vector u here. And of course, if I do the parallelogram law there, you see that w actually ends up being the resultant vector for that. So that is important because what we want to do here, let me erase all of this. So what we want to do here is we want to use that in our derivation to figure out what our angle theta is going to be. All right, so let's go ahead and move on. All right, so we're back here, and there's a couple things we need to take into account. First thing, like we mentioned before, the magnitude of u, the magnitude of v, and the magnitude of w, they are all, in this case, going to be what the lengths of the sides are. Okay. Now, of course, we know that calculating the magnitude of a vector that has 3 components to it is just going to be the sum of the squares of all the components, and then you take the square root of it. So, of course, if we square those results, it's just going to be the expression that's under the radicand here. Okay, and that works for both magnitude of u, v, and w. As we mentioned before, the vector w is really just the vector u minus v. And of course, u minus v is, if we broke that up into components, it's just going to be u1 minus v1, u2 minus v2, and u3 minus v3 for both its x, y, and z component. So because of that, we know that the component w1 is just u1 minus v1, w2 is just u2 minus v2, and w3 is equal to u3 minus v3. Okay. Thus, the magnitude of w squared is just going to be all of these components that we see here squared. And of course, since these are actual scalar values here, if we knew what u1 and v1 were, of course, we could just subtract them and then square. But since we don't, we got to kind of treat it like how we would if we were dealing with quadratic functions and multiply this out by using the Ferrell method. Okay, so if we do that for all 3 terms here, what you see is that we end up getting this result here. And again, that's just taking u1 minus v1, multiplying it times itself, doing a from method, getting your result. And the same thing for the other two. Now, the important thing to note here is that remember that the magnitude of W squared is the sum of all three of these. So now if we look down here, we will see that now we're actually taking the original equation that we had and rearranged it. I'll kind of go back to make sure that you follow that. So this is what we originally came up with the law of cosines if we rewrote everything in terms of vector magnitudes. And if I rearrange this to solve for 2 times the magnitude of u times the magnitude of v cosine theta, then of course that ends up looking like what you see here. Okay, and so now that we kind of know what the magnitude of u, v, and w squared actually looks like, we can actually plug this into our equation here and try to simplify. Okay, so if I do that, then of course we know that the magnitude of vector u squared is just going to be this u1 squared plus u2 squared plus u3 squared. Same thing for magnitude of v squared is going to be these 3 terms. Okay. Now notice that this last term here is minus magnitude of w squared. Okay. And remember that magnitude of vector w squared is the sum of all 3 of these, which is just the sum of all 3 of these here, but it's minus. So we would have to say minus this, which means minus, minus, plus, here minus, minus, plus, and then here minus, minus, and plus. And of course, if we implement that down here, then you'll see that for the U1s and V1, or U1, U2, U3, V1, V2, and V3, all those squared, that would be what you're seeing here. Okay. So we got your minus U1 squared minus U2 squared minus U3 squared minus V1 squared minus V2 squared minus V3 squared. So that's all these. And the only thing that's left are these 3 terms here. Okay. So now from this point, it's just basic simple algebra. So we just rewrite what we have left. We see that if I was to divide both sides by 2, that would reduce to 1. And then if I solve for cosine theta here, that means I would have to take this quantity and divide it by both sides, and I end up with what I have here. Okay. Now, if you recall, what this square root is here is just the magnitude of u. And what this square root expression is just the magnitude of v. So if we look at that, and we actually do the arc cosine or cosine inverse, we see that the only thing that's not written in terms of just a vector is this particular quantity here. And of course, those are all component values being multiplied by each other and then added. So that's going to be a scalar value or real number value. And so we see here that we've learned that in, of course, 3D space, this is what the dot product is. Okay. And so you can see now how we actually end up coming up with what this dot product is. It's just an operation of convenience out of the fact that we would like to be able to express that expression in terms of vectors instead of scalar components. Okay. And so that's essentially all it is. Okay. So of course our main takeaway here is that the dot product, of course, is going to be a scalar quantity. Looks like this for 2D space. Looks like, looks like that for 3D space. And we know that in trying to figure out what is going to be the angle in between 2 sides of an oblique triangle, The dot product is just this quantity here. Of course, we're talking about 3D space, and it's just an operational convenience for it. Okay. All right, so now that we understand what the dot product is, where it actually comes from, we also saw that in this derivation, we could actually come up with an alternative way of being able to express the dot product. Okay, so recall here that this is how we originally come up with what the angle is going to be in between two vectors u and v. And we recall here that, hey, in terms of the dot product, we could express this expression in the numerator as just u dot v. Okay. Now, if I take the cosine of both sides here, I will get this equation. And if I solve for u dot v, then notice here that that is just the product of the magnitudes of both vectors u and v times cosine theta. Okay. And so my point here is that this is an alternative way to be able to express the dot product of vectors u and v in terms of the angle at which those two vectors make with each other. Okay. And so this is why I say that we can figure out, back in my example, how much that new magnitude would be for the new vector along the path of v once that force strike the ball with a certain magnitude. Okay, and to be clear here, u would actually represent the force that is acting on the ball. V would be the vector that's in the path with the ball's current velocity. And so if I took the product of the magnitude of u times cosine theta, what that would actually be is the portion of the magnitude of the vector u that would actually be applied to the vector v. Okay. And of course, we're going to formally call that something a little bit later on. But right now, that's how we're just going to describe it. Okay. So main point here is that we could express the dot product as magnitude of products of u and v times cosine theta, or we could look at it, in other ways. Okay, we can just look at it in terms of its scalar components, which would be like this or like this. Okay, and so we use whichever form is going to be advantageous to us, based upon what information we already have. Okay. All right, and so again, all I mentioned here is basically what I was saying about the example with the ball and the force that acts on the ball. Of course, in terms of that example, F, whether it's F1 or F2, is going to be the force that acts on the ball. V is going to be the actual velocity of the ball along some certain path. Okay. All right, so we've talked about where the dot product comes from, what it is, the motivating, I guess, phenomenon, from normal everyday life, in a very general way of why we even need an operation like this. So now let's look at some common applications of the dot product, meaning what are situations where we actually use the dot product to be able to figure out something. Okay. Now, of course, we know that find the angle in between two vectors. We know that from the example that we had, that's going to be an application of it. And so I only do commentary here to try to make my point that if we know what the angle is in between two vectors, this angle will directly communicate what portion of the magnitude of the vector u, meaning the one that's going to act on the vector v here, that knowing that angle can directly communicate or indirectly communicate what portion of it. So we know because of cosine theta, that's normally going to be values in between -1 and 1. And because of that, we could sort of look at, if we know what the angle is, if we do the cosine of that, that's going to give us a certain percentage. Okay. Where, of course, the top percentage would be 100% in the same direction as the vector that we're acting on. Of course, on the flip side of that would be negative 100%, which is just 100% in the opposite direction. And then, of course, lowest would be, in magnitude wise, would be 0%. Okay. So none of the force that acts on that particular vector or ball would actually be none of the magnitude would be transferred to that other vector. Okay. So we know that if our vector has some fixed magnitude that we know of, and it's going to, and we only know that we want to, let's say, transfer over half of what the magnitude of the vector that's going to act on the ball would be, then we would have to know, all right, well, at what angle are you going to hit it at to make sure that that happens? Okay. So that's why knowing what the angle in between two vectors is so important. Okay. Now, traditionally, we would use law of cosines to, calculate things like, the side of an oblique triangle, or find the angle in between two sides of an oblique triangle. Now, of course, if we can write everything in terms of vectors, we can do those calculations without having to do it in the traditional law of cosine identity form. Okay. These next two points that I bring up, which are find a portion of the magnitude of some vector u that acts on another vector v, and find the updated version of the vector v that has been acted upon by the vector u, that really goes back to this first point here. I am just explicitly listing, all right, well, what are those things that we'll actually find? Okay. And another reason why I list this is because, of course, in this case of the updated version of the vector v, we're actually going to end up calling that the projection of a vector u onto another vector v. Okay. So the projection of the force that acted on the ball onto the ball. Okay, essentially. And of course here, if we want to find just the scalar or real number value component of the updated version of this vector, again, that's just trying to find the scalar component or the new magnitude of this vector v. Okay. And of course, the scalar component will be contributed by that vector u. So in other words, a portion of u's magnitude is going to be transferred over to the vector v. And because of that, that new vector for the ball would actually have a new updated magnitude. Okay. The last common example that I'll go over here is the concept of work. And of course, if you've been in any physics course or any course where you've had to calculate work, then of course we know that work is just force times distance. And naturally speaking here, force is going to be a magnitude in some direction. So we could look at that as a vector. And of course, distance, if you're going a distance in a certain direction, you could look at that as a vector as well. So if you could express both your force and your distance as a vector, then of course you could calculate work in terms of vectors. Okay. Now, the example picture that I have here to talk about this whole notion of a projection of some vector u onto v is shown here. And basically what this is saying is this. If, let's say this is some box and this box has some weight on it, really doesn't matter whether it has weight or not. It's just we have some box and we're trying to pull it. Okay. If we pull it, we know that this angle in between here would be theta. And so depending upon the measure of this angle, that would depict how much force we're actually using to be able to pull this box forward here. Okay. And of course, with this angle, we see that the box is going to go forward as long as this angle is at a certain measure, really in between 0 and 90 strictly. And depending upon what the angle measure is, that will tell us how much of this actual force is actually used to pull the box forward. Okay. Now, to kind of make my point here, let's assume that this person is pulling the box straight up, okay? In other words, it's making a 90-degree angle with this vector v here, okay? If I'm pulling the box straight up, then of course the box is not going to move to the right at all at that point, because none of the force that I'm applying is going to be applied in the positive x direction to make the box move to the right, okay? And so we'll see when we start to study the properties of dot product that this sort of thing pops up here, okay? Now, we can also look at, well, what happens if the angle in between, the vector u and the vector v actually ends up being 0? And let me get rid of this here. So let's say if u is lying in the same direction as v, okay? So in this sense, we know that all of the force of u, or all of the magnitude of u, will be applied in the direction of v, okay? So in this case, the new magnitude of it would be absolute value of u times absolute value of v, okay? Because again, cosine of 0 degrees is just going to be 1. And so 1 times whatever this magnitude is just that magnitude, okay? So you see the extremes there, that if the force is vertical, then of course none of this force is going to be applied to making the box go in the positive x direction. If the angle is 0 degrees, then of course all of it will. And of course, the other extreme here is, what if the person is pulling the box in the same, directly opposite in the direction of the way in which we're trying to pull the box, okay? That we want the box to go, okay? And in that case, of course, it's going to be this product of magnitudes of u and v, but now it's going to be minus. Because here we know that the angle in between there and there is going to be 180. And of course, cosine of 180 degrees is minus 1, okay? And again, we'll formally state all of this moving forward. So the visual interpretation of work. Notice that if we have some force pulling on a box at a certain angle here, then of course, like I've said before, depending upon the angle, that lets us know how much of the actual force or the magnitude of this force will actually be applied in the positive x direction here. And of course, this cosine of theta, that's an indirect way of telling you the percentage of how much of that force, of the magnitude of this force, is actually going to be applied in the positive x direction here. And as far as the distance is concerned, remember again, vector is defined as a directed line segment with a starting point, initial point, and a terminal point. So we could look at distance in a certain direction as a vector, okay? Now, the final two things that we need to do in this video is to talk about the properties of the dot product, and then go into detail on defining from a computational standpoint what is it that we're saying when we talk about the projection of a vector onto another vector, okay? So we know what the dot product operation is, where it comes from, where its motivation for its existence come from, and some general applications. So now what we're going to do is summarize how vectors are going to behave with each other by summarizing in a list of known properties. And so, like I've said in other videos that you probably watched, if you're watching this one, that when we introduce a concept in mathematics, there is this common format that's used. The first thing that we do is we say, all right, here's what this particular concept is. We try to give you some practical example of what it is to sort of wrap your head around it. We identify some basic things that kind of goes along with this concept. We try to work out all the nuances. But then But then after that, of course, there are basic definitions that we need to establish so that you know exactly what this element that we're working with is and what it isn't. And then after that, we say, all right, well, now that we know all that stuff, we need to tell you what the rules are of the game. And of course, with dot product, the list that we're about to go over now are the rules of the game. So if we let u, v, and w be any set of vectors, okay, so just random vectors, and this could be 2D space, 3D space, you know, onward, and we let c be a real number. And of course, if we remember, in the world of vectors, we call real numbers scalars. Then we know that the following is true as far as how vectors interact with each other. Well, number one, we see that the commutative property for the dot product acts just like how the commutative property for multiplication of real numbers acts. Okay, so in short, we know within the real numbers, we know that 2 times 3 is the same thing as 3 times 2. And what we're saying here is that with the dot product, since both of these outcomes here are scalars, meaning they're real numbers, this whole property of 2 times 3 is equal to 3 times 2 should hold. Okay, and we see that under the rules of the dot product, that is the case. For rule number 2, we see that if we take a constant multiple of some vector and we dot it with another vector, then it doesn't matter whether that constant is applied to the vector u, or if it's applied to the vector v, or if we do the u dot v operation first and then multiply that scalar answer by this constant c, it'll all end up being the same thing. Okay. Now, in a more formal sense, what I'm saying is that the associative property of the dot product interacting with scalar multiplication holds. Okay. Now, the reason I say that is because it is not a pure associative property for the dot product. This is what the associative property for the dot product would actually look like if it acted the same way that it would within the real numbers. However, we're not able to do that. In other words, the dot product won't follow the associative property under multiplication the same way that it does for real numbers. The reason why is because if we try to do this operation here, basically taking these two vectors and dotting them together and then dotting it with another vector, we're going to have a problem. And that's mainly because remember that the outcome or result of dotting two vectors together is going to be a scalar. Okay. So for example here, if I let u and v be two vectors written in component form, and w, if I was to do v dot w first, notice that what I get here is a scalar. Okay. And if I take a scalar and try to dot it with a vector, that doesn't make sense to the dot product operation, because remember, whenever we say u dot v, we know that both of these are vectors, and that's how it's defined. The dot product can't do anything with this if this is actually a real number. Okay, it looks at it and says, I don't know what that is, so I can't work with it. Okay. So that's why we don't have a true, or I shouldn't say true, but why we don't have an associative property that looks like this. We don't have that within the vectors using the dot product operation because of this fact. Okay. All right. So moving forward here, rule number 3 tells us how we deal with the dot product in the distributive property. And so we see that the dot product can be distributed over vector addition here, just like how it would be within the real numbers. Okay, so that's not an issue. And of course, again, that should be true because the fact that if we're dotting a vector with another vector, that output is going to be a scalar or a real number anyway. So all the stuff that normally happens under the real number should hold in that particular sense. Okay. Now, rule number 4 is if you take a vector and you dot it times itself, you just get the square of its magnitude. Okay. And I will just leave it at that. And of course, if we take the 0 vector and we multiply it, the 0 vector and we dot it with any vector u, then we're going to get the scalar value of 0. Okay. So please do not mistake this. When we dot these two together, we don't get the 0 vector. What we get is the actual real number 0. Okay. And again, that makes sense because we know that the outcome of a dot product should be a scalar value anyway. Okay. Now, special cases for the dot product. I actually already mentioned this, but I'm going to formally go over it again. So if you remember the scenario where I had the picture of the box and I said, hey, if we were pulling with the force that was at a right angle with the direction of where the box was trying to go, then of course no force would be applied moving in the positive x direction. If the angle in between the direction of the box and the actual force was 0, then we would have all of the magnitude of that force being applied in the direction of v. And of course, if we applied the force exactly 180 degrees opposite of the direction v of the box, then of course we would have all the force being applied but in a negative direction. Okay. So here, all I'm doing is saying the same thing, and I'm just getting more descriptive here because we know that if this angle theta here for u dot v, if it's exactly 90 degrees, then of course cosine of theta is going to be 0. So the dot product will end up being 0. Okay. If cosine of theta is equal to 1, that happens when theta is 0 degrees or 0 radians. Then of course, in that case, all of the magnitude will be transferred over. And of course, when theta is 180 degrees, cosine theta is -1, and all of it's transferred over, but in the opposite direction. Okay. And so the way that we summarize that is we say u dot v is going to be equal to 0 if and only if your vectors u and v are orthogonal to each other, which is a fancy way of saying that they're perpendicular to each other or they intersect each other at a right angle. If u dot v is equal to just a product of the magnitudes of u and v, this only happens if u and v have the same directional, direction angle, and that's another way of saying that the two vectors are parallel to one another and they point in the same direction. Okay. So they need to be parallel and point in the same direction. If your dot product ends up being negative and it's all of, if it's negative, the product of the magnitudes of u and v, that only happens if your vectors are parallel, but also in opposite directions of each other. So you could have a situation where this is u and this is v. Okay. And so if we wanted to dot those two vectors together, this would be the outcome. Whereas here, u dot v would be, this is u here, and this is v. Of course, they're parallel and they have the same direction on them. So if we dotted those together, that's why it would end up being this. All right, so the final topic for this video is defining what a vector projection of u onto v actually is from a computational standpoint. Okay, so if we look at what the vector projection of u onto v is, this is how we actually calculate it. Okay, and I've actually wrote it in two different ways. So the traditional way of calculating it in its nice compact form looks like this. Okay, I have broken it up into these two factors here because number one, we see that this first factor ends up being a scalar value, and we see that this second factor is actually a unit vector. Okay, now what this scalar value is here, this actually ends up being in the long run, how much of vector u, how much of the magnitude of vector u is applied to vector v in the direction of, okay? So that's what this particular calculation actually is here. And so you're saying, all right, well, here's how much that new magnitude would be, and here's the direction in which that magnitude will go. And so that's really what the projection is broken down up into, okay? Now, if you look here, the scalar component of u actually ends up being the magnitude of u times cosine theta. So all this that I've shown you here, this is really just the magnitude of u cosine theta. Okay, that's just another way of writing. And again, this is a portion of the magnitude of u that is transferred to v when u acts upon v. So that's literally what this means. And that's the same thing as what you see here. So because of that, we see that the projection of some vector u onto another vector v could simply be written this way. And we would use that if we actually knew the angle in which those two vectors intersected each other or acted upon each other with, okay? If we don't know that information of, what is the actual angle, then we would probably go back to using this form of being able to calculate the projection, okay? And again, I want to make sure that whenever we talk about the projection of a vector u onto v, that actually ends up being another vector, okay? Because notice here, that is a vector. Whenever we do the scalar component, that is a real number value, okay? So the scalar component of u, that's just a real number value, okay? And of course here, this projection, this is the scalar component of it, or the real number value part, and this is the actual vector, okay? Now, one of the last things I want to mention here is the fact that the length of the projection of some vector u onto a vector v can be interpreted as being positive or negative, okay? Now, this is an important point to make because traditionally, whenever we talk about the length of something or the distance of something, we know that distance can't be negative, just like length can't be negative. But because we're talking about, in this case, length in a direction, the direction is actually important, since one of the things that's important about vectors is knowing the direction of it, okay? So that's why it's acceptable for us within the vector world to talk about lengths that are positive and negative, okay? If we want to ignore the direction of a length, if we want to put it like that, then we look at the magnitude of the corresponding vector, okay? So that's why we define what magnitude is, because magnitude ignores direction. But when we talk about length, length actually has a direction to it in the vector world, whereas magnitude does not, okay? And essentially all we're saying here is that if cosine of theta, if we know what that angle is, if it ends up being positive, then we know that that angle is in between 0 and 90 degrees. And this should actually have a degree sign on it here. Well, we include 0, but don't include 90 degrees. If cosine of that angle is negative, then it's going to be anything larger than 90 degrees up until 180. So put another way, your angle is going to be in quadrant 1 if cosine is positive. Your angle is going to be in quadrant 2 if cosine of theta is negative. And so we only consider angles from 0 degrees to 180 degrees, or if you want to look at it in radians, from 0 to pi radians, because of the fact that, remember, all of this comes from trying to find the angle in between two sides of an oblique triangle. And we know that for a triangle, the sum of all the angles in a triangle has to be 180 degrees. Okay, so because of the context of the origins of where all this stuff comes from with the dot product, it doesn't make sense for us to talk about an angle that is more than 180 degrees, or an angle outside of being in quadrants 1 and 2. Okay, if we were given an angle that would be outside of the range of 0 to 180 degrees, we would have to translate that. So let's say if we had an angle that was given in quadrant 3, we would have to look at that in terms of its reference angle with the negative x-axis and the terminal side of that particular angle in quadrant 3. So we have to look at it in those terms. Okay. All right. So this concludes my discussion on the theory behind the dot product. I know a lot was said here, but hopefully by listening to this gives you some insight as to not only what the dot product is and how to calculate it, but what is all of the underlying thinking that goes along with the dot product. Okay. Now, the next video that I'll do is I'll just simply go over examples of utilizing the dot product. And so I hope to see you there.